All right, let's take a look at part A. So one thing I'd like for you to have a habit of is seeing what happens if you just try direct substitution, like brutally treat this limit as if it's a function value. So let's say we just plug the 3 in for part A. We'd have 3 minus 3 on the top, which is 0. And then we'd have 3 squared minus 9 on the bottom, which is also 0. So now let's talk about 0 divided by 0. There's so many things 0 divided by 0 can be. And it all has to do with as you plug in numbers infinitely close to 3, how fast are you approaching 0 on the top? And how fast are you approaching the value of 0 down there in the denominator? And how do those two values compare when you're getting infinitely close to plugging in a number like 3? So like what happens when you plug in 2.99999? And so, or 3.00001. And so the idea is that you're dividing two numbers that aren't actually 0, so they will have some value to them. And then how do they divide out? Okay, so with that said, remember that 0 divided by 0 is what's called an indeterminate form. Okay, so the technique that I believe we had learned in this case earlier in the year was to just kind of use a factoring and canceling technique. So here we go. You'd be left with, the limit as x approaches 3 of 1 over x plus 3. And then now try direct substitution again after that common factor canceled out, and you'd be left with 1/6. There we go. Okay, so let's look back up at this indeterminate form that we had. So basically the idea is that you had a number that was approaching 0 on the top and a number that was approaching 0 on the bottom, but maybe the numbers were looking kind of like this, like, they compared to each other like this. So that's what when we say 0 equals 0 over 0, it doesn't really equal 0 over 0. It equals a number infinitely close to 0 divided by another 1. And then in this case, you can see that the ratio of those numbers was 1/6. So the number on the top, let's see, how would I say this? The number on the top is approaching 0 6 times faster than the number on the bottom. There you go. Okay, and then I'll add in that is indeterminate. Okay, now let's go ahead and see what happens with part B. First, by using, very grossly using direct substitution. As if infinity is a number, right? Anyway, so let's say you have infinity squared times 10 minus 1. You'd have infinity. And on the bottom, infinity squared times 2 plus 1 is also infinity. And what's infinity divided by infinity? Nobody knows, because it depends on how fast you're approaching infinity. The number on the top is getting infinitely large in magnitude, but what if it's doing it 5 times faster than the number on the bottom is? So the point is that this is also an indeterminate form. So indeterminate form means we don't know yet. To be determined, basically. Try something else. Okay. And what could that something else be? Oh my goodness, so many things. There's, long division. There's all sorts of different techniques. I think the technique that most people would be familiar with that we had learned for an infinite limit was to multiply by a creative version of 1, where the degree on x there would match the degree of the denominator. And then distribute that in and cancel as you go. So you'd end up with 10 minus 10, minus, not 10, 1 over x squared over 2 plus 1 over x squared. And then try again. So let x, approach infinity. So, here you'd have 1 over infinity squared. So this entire piece would approach 0. Hopefully that makes sense. And the same thing here, this entire fraction would approach a value of 0 because you'd have 1 divided by this number getting so large in magnitude. So anyway, so you'd be left with 10 minus 0 over 2 plus 0, also known as 5. There we go. So what does that tell us? It tells us that this top value was approaching infinity at a rate 5 times faster than the bottom one was. So, for example, maybe the top number was approaching, you know, a 1 with 1, 2, 3, 4, 5, 6 zeros after it, over a 2 with 1, 2, 3, 4, 5 zeros after it. I don't know. Anyway, you know, and every time add a 0 here, you add a 0 here. So you have a number that's approaching infinity on the top. See, look, there we go. Anyway, you have a number approaching infinity on the top, one approaching infinity on the bottom. It's just the one on the top is growing 5 times faster than the one on the bottom. So there you go. I'll put this back. Okay, so at this point, I hope you're feeling like you're getting a nice review of some basic evaluating limit techniques, and then also a review of what indeterminate forms meant. Okay, moving on to part C. Let's see, let x approach infinity. Oh, come on now. Anyway, you'd have 1 minus e to the 2 times infinity. So what would that be? Negative infinity. And then 1 minus e to the infinity. That'll be over negative infinity. And as tempting as it is to cancel these out and say the answer would be positive 1, remind yourself that this is an indeterminate form because it depends on how fast each of those values is approaching negative infinity as far as like what you'll get when you divide them. Okay, so for this one, I think you could fall back on factor and cancel. The top right here, this is a difference of 2 squares. It's equal to 1 plus e to the x times 1 minus e to the x. And you'd be left with the limit as x approaches infinity of 1 plus e to the x. And then let's let x approach infinity now on this, and you'd have 1 plus e to multiplied by itself infinitely many times. And so you'd end up with infinity. And so what does that tell us? It tells us this top number is growing infinitely faster. How would I word that? Infinitely many times faster than the number there on the bottom. So hopefully that makes sense. They're both approaching infinity, but the top one's doing it way faster than the bottom one. So there you go. Okay. All right, my friends, hopefully those answers make sense. Before we talk about the next example, let's talk about what L'Hopital's rule is and when you should use it, okay? So at this time, let's summarize some very common indeterminate forms, and you'll see why in a second. So we're talking about within a limit, you know. So if you end up with 0 over 0, that's an indeterminate form. Infinity over infinity, very common. And then just kind of like different versions of infinity divided by infinity. You could have positive infinity divided by negative infinity, or negative infinity divided by positive infinity. And these are really the most common indeterminate forms. We're going to have some more coming up. But hopefully it makes sense that if you get these when you try direct substitution within a limit, that you're going to need to try something else to figure out what the answer is. Okay. Now let's move from there and talk about L'Hopital's rule. Okay, so L'Hopital's rule says if the limit as x approaches c of one function of x divided by another one, if it is indeterminate, then you can actually get the answer in a different way. And I was alluding to it when I was explaining the idea behind the warm-up. So let's look up the warm-up really quick. For part B, that's an easy one to kind of look at. We got 5 because the value, that number on the top, it was approaching infinity 5 times faster than the number on the bottom. So L'Hopital's rule basically is a way to figure out the value of the limit by comparing the rates. And so let's think really quick, like what calculus concept do we have that represents the rate of change of a value? Yeah, the derivative. So the limit as x approaches z of c of f of x over g of x. If it's an indeterminate form, then you could get the value of it. So I'm just writing that again. The limit as x approaches c of f of x over g of x would be the same as the limit as x approaches c of the rate of change of the value of the top function divided by the rate of change of the value of the bottom function. There we go. And that's it. That's L'Hopital's rule. There we go. We'll give it a special cloud because it's a big deal. Bigger deal than the cloud on the left there. But knowing what your indeterminate forms are is really important because you should not be applying L'Hopital's rule unless you have an indeterminate form. So you don't have the green light to use that equation there at the bottom unless you've checked to make sure you actually have an indeterminate form. And at some point in this lesson, we'll kind of show you how you could get burned if you don't check for that condition there. But for now, just try to remember it. All right, my friends, example 1. I'd like for you to redo each problem from today's warm-up using L'Hopital's rule. And I've copied those 3 problems down here. I'll do part A with you, and then I'll leave you on your own to think about parts B and C. So for part A, the first thing you do is just like last time, try direct substitution and verify that you do have an indeterminate form. If you do, then, and watch this, my friends, over your equal sign, you're going to put an L'H. It's the way that you tell yourself and the world that you're applying L'Hopital's rule. So if you do have an indeterminate form, then the original limit should be equal to the limit as x approaches, the same target number, over the derivative of the numerator. And so what's the derivative of x minus 3? It's 1. Divided by the derivative of the denominator, which would be 2x in this case. And then try direct substitution again, and you'd end up with 1 over 2 times 3, also known as 1/6. There we go. And why does that work? Because you're comparing the rate at which the top number approaches 0 to the rate at which the bottom number approaches 0. So hopefully that makes sense. All right, my friends, see how it goes with parts B and C? Check in with me in the next video.